In the IB Physics curriculum, there are three main topics: energy, forces, and motion. This video is about motion. Now, when we talk about motion, really, we're referencing how fast something is moving relative to some reference point. And we typically describe that how fast as a velocity. Note that acceleration is a part of this, is how fast the velocity is changing. But the primary unit of motion is how fast it's moving in meters per second, how that motion is changing. All of these equations here have some sort of how fast, some sort of velocity represented in them. These aren't really all of the equations that represent velocity, but some of the big ones that you might see in terms of this concept of motion. So let's look at some of this. And really, a big aspect of this is this idea of graphing. So this is a good opportunity to review some of the rules that we know about how units are formed by looking at a graph. If you have a motion graph here representing the velocity versus time, some major things that you can do to this motion graph. First, you could find the slope. In this case, if you ever find slope, it's your y divided by the x. In this case, you can take units and plug them in. So meters per second divided by seconds, well, that's just going to be meters per second squared, which means that the slope is another way of finding acceleration if you are looking at a velocity versus time graph, meters per second per second. Another thing that you might do to a graph like this is find the area. Sometimes we call this the area under the curve. Really, it's the area bounded by the x-axis. So here we see the area represented there. Now, if you ever find area, it's the same thing as finding the area of that shape, which is taking x times y. If I do the units now, meters per second times seconds, the seconds are going to cancel out, and I'm left with just meters. Meters is a way of figuring out how far you went. It's your displacement. Which means in this graph, I could figure out the total displacement by finding the area. I could find the acceleration of the graph by looking at the slope of that line. I could also just find velocity by reading it. I could say, what's the velocity at 2 seconds? Well, at 2 seconds is simply a velocity of 3 meters per second. So one graph can tell you a lot about an object's motion. You can also use these same ideas, finding some unknown here in a graph that doesn't really have anything to do specifically with motion. So here, if I wanted to find the area of this graph, well, again, my rule for area was the units are just going to be whatever the x is times whatever the y is. Here it's seconds times newtons, or force and time multiplied together. You might remember there is a concept called impulse that is just force times the change in time. So when you find the area here, you're finding the impulse. And remember, when you find the impulse, you're finding your change in momentum. So knowing an area or knowing a slope can often lead you to other things. And if you were trying to figure out how did the velocity change of this, you might look at that and say, I have no idea how the velocity changed because velocity isn't on this graph. But if you're clever and note that force and time multiplied together is just the impulse, and impulse is a change in momentum, if you know the mass, you could figure out how the momentum changes by looking at the impulse and find a final velocity that way. Here, we can do the same thing. We can see what the area is on this graph. Well, the area on this graph is force times displacement. You might remember a little quantity called work is the force times displacement. That's another way of getting your change in energy. And that's the work energy theorem. So if you can find the area under the graph, you can figure out how the energy changes. That can be useful if you're trying to find how the energy is changing on an elastic spring. That's a very similar graph here, as that force changes the farther you pull it. That could also be useful if you're trying to figure out how fast something is going and you're pushing a cart at a variable force. You can use the area to figure out that change in energy and solve for an unknown that way. All right, another concept looking at motion is simple harmonic motion. You might remember that there are three major graphs related to simple harmonic motion. Here it's displacement, velocity, and acceleration. If we are looking at an object that's oscillating, so something that's just moving up and down in a repeating pattern, this graph here for displacement is starting with the object at the bottom, moving up, getting to the top, moving down, and it's oscillating between these two maxima position, um, a negative displacement and a positive displacement. Well, to find the velocity, we can look at the slope. So anytime the slope of this graph is 0, means that at that instant, the velocity is 0. If something's oscillating up and down, these are the points that it's changing direction. So 0, 0, 0, 0 at its highest and lowest point. So I know that the velocity there at those points is going to be 0. Now, when we are passing through the center, we are either moving upward or we're moving downward at our maximum velocity. To know which one it is, just look at the slope. Slope is positive, so that's a positive velocity. Negative is a negative velocity, positive is a positive velocity, and so on. We get a velocity graph that looks something like this. We can do the exact same thing to find our acceleration. So find where the velocity graph has a 0 slope, and that is your 0 acceleration. If it's a positive slope, that's a positive acceleration, and so on. We can build this graph in the same way that we did before. Pardon my messy graph. And one of the things that you'll notice here is that the displacement graph and the acceleration graph are exactly opposites of each other. We can say that the acceleration is proportional to the inverse of the displacement. So the acceleration is always going to be opposite the displacement. If you're at the bottom, you're accelerating upward. If you're at the top, you're going to accelerate downward, and vice versa. That acceleration is just trying to restore it back to its initial position. Now, if we're trying to represent these graphs in a clever way, putting displacement on the x-axis, we can do that. Remember here, displacement is maximum, is it really negative or really positive at its lowest and highest point? And we said at the lowest, highest point, that velocity was 0. That was the turnaround spot. So we can say displacement at its maximum is going to give us a velocity of 0. And then when it passed through the middle, we call that a displacement of 0. It was either moving up or moving down at its fastest possible velocity, which means you could have more than one velocity depending on which direction you're going. And we get a graph that looks something like this, which is kind of strange to see that in a graph. But what's happening is that motion, if we were to trace what's going on with that graph, it's really just moving around this graph the entire time. Now, if we were trying to find the acceleration in displacement, remember that a negative displacement gives us a positive acceleration. So a negative displacement is a positive acceleration, and a positive displacement is a negative acceleration. In the middle, there is no acceleration. So we see a graph that looks like this. So just like I animated the first one, we can animate this one. It's just moving back and forth as it's oscillating in this simple harmonic motion. So these are those two graphs. Again, we don't need them represented again. All right, now talking about waves, another example of motion is how the wave moves through space. In this case, the wave speed is represented by a c. That's technically the speed of light, but it could work with any wave, and that will give you the frequency times the wavelength. And one of the big ways that we combined this equation with some other things that we knew was looking at standing waves and how instruments produce notes. Well, a standing wave is a wave that looks something like this. The way we draw it is that wave oscillating between two different positions. Now, really, we're not seeing both of these at the same time. We're seeing here a red and a green. They're just oscillating between these two different positions. And the number of standing waves is really counting the number of what we call antinodes in this wave, this maximum. So we would call that 4 standing waves. But that is not really 4 complete wavelengths because, remember, this is not both of these at the same time. If I were to erase one of these and just look at one side, one complete wavelength is this part here. So that's one complete wavelength, which means that this graph shows me one complete wavelength there, and then this next part is one complete wavelength as well. So in this particular picture, there are 2 complete waves. Or let's say 2 complete wavelengths. All right, well, I'm going to draw in the other side of that standing wave again, just so that we can see that, and then I'm going to minimize this so that we have more space to talk. Well, if I draw a big standing wave again, we can use our understanding of this to figure out what's going on in these different situations. An open pipe system is one that is resonating with an antinode on both sides. A closed pipe system is one side closed and the other side open so that the air can still vibrate. We'll have a node on the closed side and an antinode on the open side. And for a string, we have a node and a node. Now, what that looks like in the simplest possible framing of it is really looking at the standing wave. If I started with an antinode here, the simplest possible wave would be finding the next antinode. So if I were just sweeping this across until I hit an antinode, oh, it's right there. So my simplest possible wave looks something like this. That is half of a complete wavelength. So in this case, we would say that the length of this wave is equal to half of a wavelength. Now, I could find the next harmonic that would show up by just moving this along until I get to the next standing wave, or the next antinode. So it would look something like this. That is also an open pipe system, but now instead of half of a wavelength, I'm actually seeing one complete wavelength. So this length would be one wavelength. It's the same. Now, if I were trying to do this for a closed pipe system, well, I am not going to start at an antinode. Instead, I'm going to start here at a node. Then I'm going to move this along until I hit an antinode. Oh, I hit one right there. So this is my simplest form. If I were to find my next simplest form, I keep going until I hit the next antinode. Oh, it's right there. So that next simplest form is going to look something like this. Now I can do the same thing to figure out how the length of the instrument corresponds to the wavelength. The length here is 1/4 of a wavelength, and the length here is 3/4 of a wavelength. To do a string, it's the exact same thing, only we're going to do node and node. So first harmonic, second harmonic, looks something like that. Our rules are exactly the same as the closed or open pipe system. It's half a wavelength and a full wavelength. Now, you are not expected to memorize these drawings. What you should remember are these conditions: node, antinode, 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 node, node, and how you would draw that standing wave. And then from a drawing of a standing wave, be able to say, okay, here's how many complete wavelengths there are and what the standing wave would be. All right, another way that we saw the motion of a wave is through this idea of refraction and how light can travel from one medium to another. When it does that, it changes its direction. And the reason it changes its direction is because light moves slower in certain media. So if we go from air to glass, light slows down. The way we talk about how much slower it's going is through something called the index of refraction, this N value. You can relate the index of refraction directly to how fast it is moving using the equation N1 over N2 is equal to V2 over V1. Just ignore this middle part entirely. We can also use this, though, to figure out how the angle changes. That's that middle part. Well, the conceptual model that we talked about in class is this one. Imagine that you have a 2-wheeled cart that is going from something that moves fast to something that moves slow, air into glass. Well, if that happens, and if I were to animate that here, it's moving, moving, moving. One wheel hits the glass first and slows down, while the other wheel keeps going the same speed until it also hits, and they can move off in the same direction together. Again, moving, 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 slows down and kind of jerks it in towards that center line. We will draw that kind of deflecting inward towards that normal line. Remember, the angles here are the angle between the refracted or the ray and that middle line. We call it the normal line. Now, if we went from air or water to air, trying to escape, we could see a similar sort of picture. Trying to animate that here. We're going from something slow to something that's fast. So normally it would go like this, that one would escape and move outward and would bend kind of away from the normal line like that. When you are going from a more dense to a less dense media, there is a chance that you might have a situation where it deflects so much that it's actually right along the surface, where this angle here, theta 2, is equal to 90 degrees. If that's the case, that's called something called the critical angle. And the critical angle is at which it's no longer able to escape. So if you go beyond the critical angle, it'll just bounce right back in with total internal reflection. All right, our last topic that we're going to look at motion of something is electricity. Electricity, our motion was primarily the motion of charges. Now this equation here is our equation for something that we call drift velocity, or drift speed rather. And drift speed is figuring out how fast an electron is moving through a wire. That's what this V stands for. It's how fast the electron is moving. Well, in this case, there are a lot of different things that are factoring into that. Q is the charge. It's how much charge one particular electron has. Typically, if you're talking about a single electron, the charge is the elementary charge. In the data booklet, E is provided to be 1.60 times 10 to the negative 19th coulombs. So that's how much charge a single electron would have. A is the cross-sectional area of the wire. Typically, that's going to be given as pi r squared. It's usually going to be a circle. It might not be, but it's usually a circle. And N is talking about how many electrons there are in a given amount of wire. All of that together will give you a current, I. I is given to you in amps, and you can use that current to help you figure out voltage, resistance, even power, talking about a circuit. So, thinking about circuits, let's do one circuit to just remind ourselves some of the tools that we have for solving that. So a couple of skills here. This is a common circuit example that's called a potential divider. It's a way of splitting up the voltage and making a smaller voltage. So here, if you are giving something 10 volts, giving the circuit 10 volts of voltage, the voltage out here, if you were to connect something over one of the two resistors, is going to be smaller than this voltage in. So it's a way of dropping that voltage down. Now, figuring out how much that voltage is going to drop down, you need to compare these resistors. The size of the resistor is really going to talk about how much voltage is dissipated here. So the smaller resistor is going to dissipate less voltage than the larger resistor. And in this case, this V out is represented, that's a voltmeter, is the way that it's drawn. And a voltmeter ideally will have a resistance of infinity ohms and will not let any current go through it, which means that we can kind of ignore it in terms of this circuit. So this kind of looks like a complicated circuit, but it's not. It's just a simple circuit of two resistors. And since it's a simple circuit, that current is going to be flowing through the circuit like this. Whatever goes through one is going to flow through another. And to do this, we're first going to need to figure out what is the overall resistance. Combined, these two are in series, so they just add up. 220 plus 30 gives you 250 ohms. Now, we know from Ohm's law, voltage is equal to current times resistance, which means that the current is voltage divided by resistance, or 10 divided by 250. Well, 10 divided by 250 will give us a current of 0.04 amps. 0.04 amps. Now, that current is the same all the way through. So it's the current coming out of the battery, but that current doesn't change as it goes through this whole thing. It doesn't split anywhere. There's no junctions, which means that every resistor along here is getting that same current, 0.04 amps. Then we can use this same Ohm's law to calculate the voltage. Voltage is just current times resistance. Well, current times resistance 0.04 times 30 is 1.2 volts. 0.04 times 220 is 8.8 volts. You'll notice that these two add up to 10 because of the voltage loop rule, meaning that the voltage dissipated equals the voltage provided. Here, this is 8.8 volts. This is 1.2 volts, which means that if I'm trying to figure out how much voltage this voltmeter is measuring, that's going to be the same as just measuring that resistor is 1.2 volts. So this is looking at motion in a slightly different way, motion of electrons. But again, motion shows up in a variety of different contexts in the IB physics curriculum. Here are lots of different examples of motion. One thing that we did not reference in this video was looking at circular motion, or really how motion factors in with energy and power. Kinetic energy incorporates motion, and then all of the Suvat kinematic equations also use motion. So this video didn't really talk about a lot of these equations, but once you know velocity, these equations can pull in exactly the same way as they would in any other simple word problem.